Greetings. So welcome to today's class. So we were looking at longitudinal dynamics during drive, and in the previous class we were looking at the longitudinal dynamics during drive from the powertrain's perspective, and then we looked at it from the perspective of the vehicle, and we considered the forces acting on the vehicle, and we considered this free body diagram, right? So this is where we stopped. So if we recall the important differences between the free body diagram that we drew for braking and the one that we are now considering for drive is the presence of this drive force at the front and the rear tire rod interfaces respectively along the direction of motion, and the fact that now the D'Alembert's force is in the opposite direction, right? D'Alembert's force is anyway a fictitious force which is in the direction opposite to that of the acceleration, and in this case it is in the direction shown here. So once again, what we do is a similar process like what we did for braking. We write three equations. The first equation is we sum all the forces along the direction of motion and equate it to be zero. Okay, so that is the first equation. The second equation is it like we take all moments about the point A and then like equate it to zero. We'll get an equation for WR. And the third equation is it like we are going to sum all moments about the point B and equate it to zero, and we'll get an equation for WF. Okay, so that is what we are going to do. All right. Let's look at what happens to these equations. Okay. So first, if we essentially do summation of all the forces along the direction of motion to be equal to zero, so what we get is m times a, which is W by G times A, is going to be equal to the sum of the two tractive forces, FF and FR. Without loss of generality, we will assume tractive forces on both the front and the tire rod interfaces, right? And then like we have a set of loads, right? Resistance forces that come up. So which includes the aerodynamic drag, the rolling resistance, and the drawbar pull and the grade resistance, right? So RRF and RRR, when put together, we will get the net rolling resistance. Okay, so this is something which we are already aware of. So we take F to be the net tractive force, FF plus FR, and RR, R subscript R to be RRF plus RRR. And then like we rewrite this equation. So this is pretty intuitive, right? So this F is the net tractive force that the powertrain should provide. And that is going to be the sum of all the loads that the powertrain needs to overcome, right? This is inertia. This is aerodynamic drag. That is one resistance force. Then we have a rolling resistance. That is another resistance force which the powertrain needs to overcome. Then we have the drawbar pull in case the vehicle is towing some other vehicle, we have the drawbar pull. And finally, we have the grade resistance, right? So in case the vehicle is going up a grade, what happens to the corresponding mg sin theta component, right? That also needs to be overcome. So these are the various loads that the powertrain needs to overcome. And when we sum them, like that is the sum is the tractive force that should be provided by the powertrain, right, to overcome these loads. So if we do moments about point, of course, so it depends on what point A and point B are, right? So we called this should be point B. So if we go back, point B was the rear tire contact point, right? So if we take moments about point B, we will get an expression for WF in this manner. And if we take moments about point A, sorry about that, we get an equation for WR. Okay, so once again, pretty standard. So we have already looked at a similar equation for braking. We are just now doing it for drive. So what is like what are these WF and WR? WF and WR once again will be the normal loads on the front and the rear wheels respectively. So we are going to do a similar process here. So once again, we take the grade angle to be small. So consequently, we'll take cos theta as to be almost equal to 1. And then like we also make this approximation HA equals HT equals H. Okay. And then like if we do these approximations, these two equations that we wrote down on the previous slide become in this manner. And then like this set of terms, right, that appear in the square bracket here is going to be F minus R subscript R, right? So that's something which we get from the equation of motion along the direction of motion, right, for translation. So we just substitute it and we get these two equations, right? So one for WF and one for WF. And just like before, we have these two components, which are the static loads, right? The static load on the front wheel is going to be WL2 by L, and the static load on the rear wheel is going to be WL1 by L, right? So this is something which we are already familiar with. Now we can observe the effect that we discussed even before, right? During braking, there was a dynamic load transfer along the longitudinal direction from the rear to the front wheels. During acceleration, there is a dynamic load transfer from the front wheels to the rear wheels. Okay, so that's what we can observe here. Okay, so this is the longitudinal load transfer. Okay, longitudinal dynamic load transfer from the front to the rear wheels. Okay, so this is something which all of us experience, right? So when the vehicle is accelerating, you know, like all of us tend to go backward, right? So we can observe that there is a dynamic load transfer from the front wheels to the rear wheels, right? So when the vehicle is being accelerated. So of course, if we sum WF and WR, obviously we get the total weight W, right? So this is something which we already are aware of. So through this derivation, what we have done is that like we have obtained expressions for the normal load on the front wheel and the normal load on the rear wheel, right? WF and WR. And we could observe that there is a longitudinal load transfer during acceleration, which takes place from the front wheels to the rear wheels. Okay, so those are important observations from this derivation. Now we are going to do a similar exercise like what we did for braking, but there are going to be subtle differences here, right? So we are going to get the maximum tractive effort available at the tire road interface. So we are going to calculate the maximum tractive effort for a front wheel drive and a rear wheel drive. Okay, so let us denote a front wheel drive vehicle by FWD. And then like what will be the maximum tractive force? It will be mu times WF. Okay, we can use mu P if you want to be consistent. So let us say we use mu P times WF, mu P being the peak tire road friction coefficient. So we just substitute for WF. Of course, here we put F max and we essentially simplify it. And then we are going to get F max to be equal to mu PW times L2 plus FRH divided by L minus mu H. So typically this component is going to be much smaller. FRH is going to be pretty small when compared to L2 in the denominator, numerator. Please note what happens in the denominator. We get what is called L plus mu PH. Okay, so that is what we are getting in the denominator. Okay, so we will come to this shortly. So what have we done? We are considering a front wheel drive vehicle. We want to find out what is the maximum tractive force available from the front wheel drive vehicle at the tire road interface. So what we do is that like we take F max to be equal to mu P times WF. We substitute for WF and then like we essentially simplify for F max, and this is what we get. So what is this expression? This expression tells us what is the maximum tractive force that we get out of a front wheel drive vehicle. Okay, so that is point number one. Now we do a similar exercise for a rear wheel drive vehicle. Okay, so let's call that as RWD. So if we take a rear wheel drive vehicle, once again, the maximum tractive force will be mu P times WR, right? So we are going to get this, we substitute for WR, and then like we rearrange for F max, and this is what we get. Okay, once again, FRH is going to be pretty small. So we are essentially going to look at what happened. So when we have a front wheel drive as opposed to a rear wheel drive. Okay, so this is the maximum tractive force that we get out of a rear wheel drive. And if we recall what happened with the case of a front wheel drive, let me write down that expression here. So F max for a front wheel drive would have been mu PW plus times L2 plus FRH divided by L plus mu PH. Okay, so this is what we would have got for a front wheel drive. So this, in some sense, like tries to give us an intuitive understanding of why we do use certain drive configurations, right, in certain classes of vehicles. Let us say we consider most passenger cars, right? In most passenger cars, what's going to happen? Like the engine, powertrain are all going to be mounted to the front, right? So consequently, the center of gravity is going to be more towards the front. So we can immediately see that L2 is going to be greater than L1, right? Why? Because the CG is more towards the front, so L1 is less than L2. Of course, like please note that if you look at the denominator of these two, formulae, we have L minus mu ph in the rear wheel drive formula and L plus mu ph in the front wheel drive formula. Of course, having L minus mu ph in the rear wheel drive formula helps, because why? That sort of increases the number, right? When you have L minus mu ph, we are going to have a smaller number in the denominator. So in a certain sense, the dynamic load transfer during acceleration, which is captured by L minus mu ph, tends to drive the maximum available tractive force higher for a rear wheel drive configuration. Okay, so that's what is happening when compared to a front wheel drive configuration. However, for most passenger cars, L2 is greater than L1, and we can immediately see that L2 appears in the formula for the front wheel drive, okay, when compared to the rear wheel drive. Okay, so that sorts of, like tells us why we drive the front wheels, because there is a larger potential for tractive force from the front wheels in the passenger car, and that's why we prefer a front wheel drive. On the other hand, let's say we consider a truck, right? In a loaded truck, most of the load is going to be on the rear wheels. So consequently, L1 is going to be greater than L2. Okay, the CG is going to shift towards the rear, and L1 is going to be greater than L2. And the value of H will also be significantly high, right? Because the height of the center of gravity will be higher in a truck. So both these factors combined together make it more meaningful for us to drive the rear wheels in a truck, right? Because we are going to have a much more potential for tractive force in the rear wheels, right? When compared to the front wheels in a truck or a bus, right? So that is why we drive that. Okay. So I hope this derivation and the corresponding expressions give us as an intuitive feel of how we choose to drive a certain set of wheels, right? So if we take, let's say, a race car, right? In a race car too, the height of the center of gravity is quite low, but then like the engine, the gear, the transmission are all placed towards the rear wheels, right? So consequently, L1 is going to be greater than L2. So obviously, we drive the rear wheels, right? We get more thrust. So that becomes very important for race cars, right? We want to sort of utilize the maximum possible thrust or the traction force available at the tire rod interface, so that like we can utilize or get the maximum possible F max. Okay. So what I want you to do as the next exercise is that like calculate F max using these two formula for the three vehicles that we looked at before. You remember we looked at vehicles 1, 2, and 3, right? And we would have seen some relevant parameters, W, L1, L2, and then like H and capital L, right? So you take mu p to be equal to 0.8 and then like evaluate F max for a front wheel drive and a rear wheel drive for all the three classes of vehicles, and then comment, okay, which wheels are going to provide us with more maximum potential tractive force, right? And then consequently comment on which wheels would be beneficial to be driven. Okay, so I hope you can do this as the next part of homework number 7. Okay, so once again, if you recall, I gave you specifications of 3 vehicles when we did lateral dynamics, right? And I asked you to calculate the understeer gradient and so on, right? So just go back to that table of parameter data and then use the relevant data to calculate the values of Fmax when the rear wheels are driven as opposed to the front wheels are driven and comment. All right. Okay. So this is the next homework problem in homework number 7. All right. Okay. Any questions on what we have discussed till now? So we have looked at the free body diagram of the vehicle. Once again, we derived the equations for WF and WR. We observed that now there is dynamic load transfer from the front wheels to the rear wheels, and then we calculated what will be the maximum tractive force that is possible for a front wheel drive configuration and the rear wheel drive configuration. Okay, so that's what we have done. Any questions on these topics before we go to the next one?
Sir, this FRH, like in the previous slide, FR is the rolling resistance.
FR is the rolling resistance coefficient. Okay, the rolling resistance is taken to be FR times W. Okay.
Okay, sir.
Sir, yeah, please go ahead.
On incline gradients, sir. Now we have considered theta will be small, but when theta is large, rear axle will be more logical for being driven, right? So, like, how can we?
Correct. So when you have an incline, obviously that mg sin theta term will play a more bigger role, right? And we sort of need to redo this derivation, right? Because we also took cos theta as to be 1. Okay.
Yeah.
Right. So please redo the derivation and try it out. Okay. That's a good point. All right.
Yeah. Okay. Yeah.
Yeah. So by the way, if I think I don't know whether I would have given the values of FR in the table. Suppose if I had not given the value of rolling resistance in the table, please take those values. You may neglect it. Let me quickly check whether I did give the values of FR or not. Okay, in that homework. Okay, yeah, I did give the values of FR. Okay, so if I recall, I had given WL, LF. LF will now be L1. Okay, please remember that LF is equal to L1. Okay, yeah. And then I would have given H, I, Z, C alpha F, C alpha R, and FR also I have given. Okay, so you can just calculate. All right. Any questions before we go move on? All right. Okay, so the last concept that I want to talk about in longitudinal dynamics is that of transmission matching. Okay, so what is this transmission matching? This involves calculating the first cut values of gear ratios, right, based on certain performance specifications. Okay, so the important performance specifications that we would be interested in when we are looking at drive would be gradability, maximum speed, of course, maximum acceleration, and so on. Okay, so what we typically do is that we are going to do when we are going to do this transmission matching is the following, right? So when we do transmission matching, we are given some specifications on all these performance requirements. Okay, let's say someone may tell us that design the transmission such that the gradability is 20%, the max speed is, let's say, 150 kilometers per hour, and so on, right? And we are given some prime mover to begin with, some base engine to begin with, right? So using that, how do we design these? Okay, so then the question is, let's say we have a n-speed gearbox. Okay, if you have an n-speed gearbox, the question is, can we calculate the n gear ratios NT1, NT2, all the way till NTN, which are the N transmission ratios. And then, of course, the final drive gear ratio, ND. Okay, so these are the parameters that we need to calculate. So typically what we will do is that like gradability is typically used to get an equation that involves the first gear, and max speed helps us in getting an equation which involves the highest gear or the nth gear. Pretty natural, right? So when we are going on a steep incline, we engage the first gear so that like we get the maximum possible thrust or or the torque, so that like we are in a position to climb up the grade. Similarly, when we are going at the highest possible speed, anyway, we are going to be in the highest gear, right? So that like we sort of like operate in the high speed regions of the prime mover, right? So that is the logic, okay, behind getting corresponding equations in this manner. So as far as gradability is concerned, as we have discussed, gradability is defined as tan theta S max. Okay, so where theta S max is the maximum angle that we need to climb. Okay, so if someone says gradability is 20%, so that means that G equals 0.2, then we can get tan theta. That can be equated to theta S max, and then like we can, sorry, tan theta S max, and then we can calculate theta S max as tan inverse of G. Okay, so that is pretty straightforward. All right. So as we mentioned, we have continuous gradability and starting gradability. Here we are going to consider continuous gradability. Starting gradability is when we have to overcome the inertia also, right? When we move from rest on a grade, that's when we need to look at starting gradability. We will consider continuous gradability. So the main load or the force which needs to be overcome by the powertrain when we are dealing with gradability specification is mg sin theta s or w sin theta s, right? Which is the component of the vehicle weight along the incline. And some people will use the rolling resistance and the aerodynamic drag also. Some will neglect the aerodynamic drag. Some may neglect the rolling resistance, right? Or some may neglect both. Okay, so you will find all combinations which are possible. So the main force is going to be this. Okay, W sin theta is going to be the primary force that we need to be interested in. And for small grade angles, typically what happens is that like tan theta s is approximately equal to sin theta s. So we have this equation where gradability is equal to F minus RR minus RA divided by W. Okay, so this is a pretty straightforward equation that we can get. Okay, so that is gradability. So now let us get the equations, right? So to do transmission matching. As we said, as we discussed, we want to get the values of NT1 through NTN and then NT. All right. So we want to essentially get the equation for the highest and the lowest gear ratios by looking at certain characteristics. Okay. So let's say we consider IC engine characteristics, and let's say this is torque. Okay. And then like this is the power characteristics. Okay, and this is the power characteristics. Typically what happens is that like we want to operate the vehicle at the highest speed when we have the vehicle or basically operating at the engine operating at the speed which is corresponding to the rated power or the maximum power of the engine. Okay, so let's say we denote that speed by omega E1, and let's say we are operating the engine at omega E1. So what's going to happen? Omega E1 divided by NTN will be the output speed of the transmission, the speed of the transmission output shaft. And then we divide it by ND, this will be the speed of the wheels. Okay, so this will be the angular speed of the wheels. And then we multiply it by the wheel radius R, okay, which will be the circumferential speed of the wheel. And then we multiply it by 1 minus I being the wheel slip ratio. Okay, During acceleration, of course, we define wheel slip ratio as lambda, if you remember. Some people will also use I for wheel slip ratio. That's why I'm introducing you to all terminologies. And when we are dealing with uh, acceleration or drive, wheel slip ratio is defined as R omega minus Vx divided by R omega. Okay, so that is why you can see that Vx we get as R omega times 1 minus I. Okay, if we simplify this expression. Okay, so this what we have derived is the speed, longitudinal speed, and that should be equal to Vmax, right, which is the maximum vehicle speed when we are going in the highest gear and when the engine speed is at omega E1. Okay, and that's how we get this equation. Rearranging this equation, we get NTN to be equal to omega E1 R 1 minus I divided by Vmax NT. All right, so I hope it is clear how we got this equation. So let me repeat. When we are looking at the higher maximum vehicle speed specification, we are going to operate at the highest speed, highest gear, and the engine is going to be operated at a speed where close to where we get the maximum power. Let's call the speed as omega E1. This expression gives us a relationship between the various parameters involved in the process, and through that we get this expression. Of course, here we can immediately see that there are two unknowns, NTN and ND. Okay, there is only one equation. Okay, so this creates interesting scenarios. We will see how to address them as we go along. So typically, what happens is that, like, if we are given the fact that the highest gear is a direct drive, when the highest gear is a direct drive, NTN becomes equal to 1, we can use this expression to find ND, but not always. So in modern transmissions where we have fifth gear, sixth gear, and so on, right? So the highest gear goes to what is called overdrive. Okay, when we go for an overdrive configuration, what happens is that we essentially the gear ratios will go less than 1. Okay, so we need to be aware of that. Okay, so we'll come back to this shortly. All right, but I hope this concept is clear how we got this particular equation. Now we are going to go forward and get an equation for the first gear. Okay, how do we get an equation for the first gear or the lowest gear? We are going to use the first gear or the lowest gear equation. We are going to use gradability. So we know that when the vehicle is going on the grade, what happens is that, like, the tractive force that needs to be provided by the powertrain is going to be it needs to overcome the grade resistance and the rolling resistance and aerodynamic drag. Okay, so we neglect aerodynamic drag. As I told you, some people will neglect aerodynamic drag, some will neglect rolling resistance, some will neglect both. Okay, but the bottom line is that, like, W sin theta S max will be the dominant one. Okay, so let's keep rolling resistance. Okay, so now how do we get an equation for this? Let us say TE max is the maximum torque which is delivered by the engine, okay, which is the rated torque, right? And we have NT1 as the first gear ratio. T max times NT1 will be the torque output at the transmission. And then we multiply it by the final drive ratio. This will be the torque output at the wheels. And then, of course, we multiply it by eta T, the transmission efficiency to take care of energy losses. And then this will be the net torque output at the wheels, and then we divide it by the wheel radius. This will be the net usable force in the first gear, and that should overcome the grade resistance W sin theta S max plus the rolling resistance, let's say FRW. Okay, so I hope it is clear how we are matching. So now I hope why it is called, this process is also called transmission matching, right? See, on the left-hand side of this equation, we have characteristics corresponding to the powertrain. On the right-hand side, we have terms which come from vehicle level perspective, okay? Same story in the previous equation also, right? When we wrote down the equation for maximum speed, right? So if we rearrange the terms, we get this equation, right? So we get an equation for NT1. So I hope it is clear how we got this particular equation. All right, so we used gradability requirement for getting an expression for NT1, and then like we use the what is the maximum speed criteria to get an equation for NTN. So now the question is, how do we get the intermediate gears? Okay, so intermediate gears, one idea is to use what is called as a geometric progression. And what is the idea behind this geometric progression? So typically what happens is the following. Okay, so once again, let me draw the torque speed and the power speed characteristics. Let's say this is the torque speed. Let's say this is the rated torque. And let's say this is the power speed characteristics. And let's say this is where we get the rated power. Let's say we call this as omega E1, sorry, NE1 in RPM, omega E1 in radians per second. Let's call this speed as NE2 and omega E2, okay, where we get. So now imagine what happens, right? So when, let's say the vehicle is starting from rest, right? So we essentially engage the gear somewhere here, and then like we go close to the high torque region, and then the speed keeps on increasing, right? Speed keeps increasing till this point where I reach the maximum power, beyond which the torque is going to also drop very drastically and the engine will drag. So what will I do? I will change the gears so that I sort of like bring back the engine's operating state to this point once again. Okay, so, and I keep on repeating the process, right? So I go from the point of high torque to the point of high power and then return back to the point of high torque when I change the gear. So that essentially will have the subsequent gear ratios to be in a geometric progression. So what is a geometric progression? If you have a, let's say if you have a set of numbers, right? If the ratio of any two successive numbers is the same, right? So that's a geometric progression. So we can see that if we consider a 4-speed gearbox, okay, let's say we consider a 4-speed gearbox, n equals 4, we have NT1, NT2, NT3, and NT4, right? So consequently, what will happen? NT2 by NT1, okay, that will be the ratio of the second and the first gear, which will be equal to NT3 by NT2, which will be equal to NT4 by NT3. And let's say we call this constant as some K subscript G. Okay, so that is the ratio between two successive gear ratios, right, in this 4-speed gearbox. Now, if we multiply these three ratios, right, let's say we multiply NT2 by NT1, and then like NT3 by NT2, and then like NT4 by NT3, we are going to get kg cube, right? Because why? Because each factor is k subscript g, right? So we get kg cube. But then this NT2 and NT2 will get cancelled, NT3 and NT3 will get cancelled. So consequently, we'll get this parameter k subscript g, which indicates the ratio of any two successive gear ratios when we upshift, okay, to be equal to the cube root of NT4 by NT1. So if I know NT4 and NT1, I can figure out K subscript G. And once I figure out K subscript G, I can go and find out NT2 and NT3. Okay, so that is the idea. In general, for a n-speed gearbox, this K subscript G will be equal to the n-1th root of NTN by NT1. Okay, so this is how we need to calculate K subscript G. So in this case, n equals 4. That's why we took the cube root of this, right? So in general, K subscript G will be the n-1th root of NTN by NT1. Okay, so that is the general equation. Okay, so if we use a 4-speed gearbox, so typically what happens is that, like by convention, the 4th gear is taken to be the direct drive. Okay, so let us say we have a 4-speed gearbox as an example. Okay, so when we have a 4-speed gearbox, we need these 5 parameters, right? NT1, NT2, NT3, NT4, and ND. So by convention, the 4th gear is taken to be the direct drive 1, right? So then we can immediately see that we can use the constraint of Vmax to get ND. Okay, we use the equation that we derived when we wrote down the specification of the maximum longitudinal speed to get ND. Because why we know NT4, right? If you go back, please note that once I know NTN, I can get ND. Okay, so that's what we are saying here, right? So, and then we essentially go and calculate NT1 from the gradability requirement. Okay, because we know ND, we essentially have the first gear engaged when we are traveling upon the maximum possible grade. So we go and calculate NT1, right? Since we know ND. And once we know NT1 and NT4 is anyway a direct drive, we know kg, right? So we can go and calculate this k subscript g, right? Which is cube root of NT4 by NT1. And once we calculate k subscript g, we can calculate NT2 and NT3, right? So that's how we can get the first cut values of the gear ratios for a 4-speed gearbox, where by convention the fourth gear corresponds to a direct drive. All right, so that's what it is. Okay, so this is the next homework problem which I want you to do, wherein this is once again part of homework number 7. Okay, wherein we can see that there is a vehicle which weighs 12 kilonewtons and it needs to be equipped with a 4-speed gearbox. We are given that the engine develops a maximum torque of 100 Newton meter. So TE max is going to be equal to 100 Newton meter. Okay, and the vehicle should reach its maximum speed of 100 kilometers per hour. So Vmax is going to be equal to 100 kilometers per hour. And when the engine is running at 3000 RPM. So this NE1, right? Of course, we need to be very careful. Omega E1 should be equal to 3000 times 2 pi by 60. Okay, radians per second. Please don't forget to multiply by 2 pi by 60. So gradability is 20%. That means G is 0.2. From here, we can calculate theta S max as tan inverse of 0.2. And it is also required that the highest drive gear corresponds to a direct drive. So that means that NT4 is equal to 1, right? And then taking the rolling radius of the wheel to be 0.3 meters, so R is 0.3. Transmission ratio to be equal to 90%, so that's eta T is 0.9. So please calculate the all the gear ratios, right, of the lowest gear, the intermediate gears, and the final drive. Okay, and with the available information, determine the intermediate gear ratios, and we can take the we are given that we can take the wheel slip ratio to be 0.1. Okay, and then like we can neglect the rolling resistance for first cut values. Okay, FR equals 0. Okay, so this is pretty straightforward, right? So you just need to use the equations that we studied till now to get the first cut gear ratios. Okay, so this process is what is called transmission matching, right? So wherein we are matching what we expect at the vehicle level to what the transmission or the powertrain can provide, right? Okay. So any questions before I pose another problem, and I'm going to leave you with a question on to ponder about. Okay, yeah. But then before we go to the question, any questions on what we have discussed?
Sir, in terms of performance matching, there's a requirement where we might have seen in vehicles also that I need 100 km per hour within 3 seconds or 4 seconds or 5 seconds. So how will match it then in case of that?
Okay, so that goes for acceleration performance, and so that we have to do some simulations and get it right with the IC engine powertrain. Because we have a multi-speed gearbox, we need to use the engine map to do the simulation and evaluate that. So this is only for first cut. You're correct. So once we get these first cut ratios, we do some adjustments and we can do some simulations to essentially check whether we are able to meet the acceleration performance. Okay. Yeah, because see, if you look at 0 to 100 kilometers per hour, let's say in 8 seconds, right? We are going to go through a range of gears, right?
Yeah.
We are going to keep on upshifting. So it is not easy to get a simple, straightforward equation like what we have done, right? So if you notice in all the equations that we have derived, we have assumed some gear right? In gradability, we will stay in the first gear, right? Maximum speed, we will stay in the nth gear. But acceleration, please note that we will be shifting across gears, right?
Yeah.
And we also need to look at the engine map, right, to get the location. So that's where we will check that one using a simulation, okay, a numerical solve.
So in this power rating graph you build, I can go much beyond this power rating also, right?
Yeah. So you mean after the peak?
Yes, after the peak we can go.
So
If I don't need any torque for the torque for my vehicle.
So what will happen is that, like, if you go beyond that, the torques that you require will fall down. Okay. If you are if you are essentially going to have loads which don't require that much of torque, you can anyway the vehicle will respond still, right? The speed will keep on increasing, right? Is it not? Okay, but by design we essentially take it slightly to the right of the maximum power point. Okay, and then we design, because see, ultimately what I need to do is that, like, I need to ensure that I calculate these numbers, right? Yeah, where do I draw the line? That's the question.
Okay, sir. Thank you.
Because see, what will happen beyond this maximum power point is that the torque will decrease very steeply. Okay, so this is the torque curve, this is the power curve, right? Yeah, the torque is going to decrease very steeply beyond that point. Okay, so that is the
Got it, sir. Thank you.
yeah. Okay. Yeah. Any other questions? No.
Sir, in this torque versus speed curve, sir, when we accelerate in the highest torque area, we feel a good increase in speed. But yeah, as you said, the torque increases. But sir, since we are connected mechanically to the wheels from the engine, and we are increasing RPM, sir, then even if the RPM is increasing, why sometimes the speed does not increase?
Can you repeat the question? No, which are, see, there is a cause and an effect, right? So if the engine RPM increases and the speed doesn't increase, that means that there is a lot of slip. That's all I can interpret. But maybe I didn't understand the question completely. Can you repeat it? No.
Yes, sir. Sir, in like when we are getting maximum torque from the engine, like we see increase in velocity. But when we are past the peak point and torque starts to decrease, but if we are giving on throttle and engine speed is also increasing, then sometimes we don't feel, or there is no increase in the vehicle velocity.
Okay.
So
You may be pressing the throttle, right? But then the engine speed is also reacting to the loads, right? It's not disconnected. Okay. See, it is not that we are controlling the engine speed independently, right? Is it not? Okay, because what will happen is that the engine speed will also be a byproduct of the loads which will come on the transmission, right? Or the power, the drive line. Correct? Yeah. So imagine, like, let's say we are past this point, right? And torque reduces, and then, like, we are going on a road, and suddenly we have a slight upgrade. Just let's picturize that scenario. What is going to happen? The speed will naturally fall down. Why? Because the load torque is now increasing, right? Is it not? Correct? So although I may be in the last highest gear, so you will see that we can press the throttle, okay, but then the vehicle will progressively slow down unless otherwise I downshift to a lower gear, right? Is it not? Then
engine speed will also
yeah, exactly, right? So I hope I was able to give an appropriate example, right, to convey that concept. So the speed, engine speed is also going to be a byproduct of the loads that come in, right? So yeah.
okay, sir.
All right. Any other questions? All right. So I'm going to leave you with something to think about. Okay. So let us now. This is something you need to think about and ponder on, right? So let us say in the same example, now I want a 5-speed gearbox. Okay, we want a 5-speed gearbox. So consequently, what are the unknowns? We have NT1 Oh, sorry. Oops. What is this? Okay. Oh, sorry about that. Oops. Let me write it a little bit down. NT2, NT3, NT4, NT5, and ND. So we need to figure out these 6 parameters now, right? So yeah. So suppose by convention, the 4th gear is taken to be a direct drive. Okay. So this NT5 will be less than 1. Okay. And that corresponds to an overdrive condition. See, we have what to say, an overdrive gear, right? So typically the first 3 gears are all what we call underdrive gears. The gear ratio is greater than 1, but then the output speed will be less than the input speed, right? So yeah. So, but let's say this 5th gear is less than 1, that corresponds to an overdrive condition, right? So we are going to get higher speeds, right, for the same input speed. So let's say we are given NT4 to be equal to 1, right? Now we have a problem, right? Why? Because if I use the max speed criteria, I get an equation which will, what to say, give me an expression for NT5 and ND. If I use gradability, I get an equation that relates NT1 and ND. Okay, so I have 2 equations, 3 unknowns, right? NT5, NT1, and ND. How do I solve this problem? Okay, so I hope my question is clear, right? So let me repeat. Let's say now, instead of a 4-speed gearbox, we are asked to design a 5-speed gearbox. See, 5 speeds, 6 speeds, and all very common, right? So with overdrive arrangements. So let's say, you know, like if we consider a 5-speed gearbox for simplicity, we have NT1, NT2, NT3, NT4, NT5, and ND. So we need to find the values of these 6 parameters. And let's say we are given that NT4 is 1. Okay, that's a direct drive. Now, as we know from the max speed criteria, if you go there, so we will be relating NTN, right? NTN in this case is NT5, right? So we will get NT5 ND to be some number. From the first gear, we will get NT1 times ND to be some number, right? So we have 2 equations, but 3 unknowns, NT1, NT5, and ND. How do we solve this problem? Okay. And then like, how do we get the first gear ratios? So please think about it. Let me know in the next class. And then like we will discuss what are some potential ways to solve this problem. I hope my question is clear, right? So we can keep on going. Let's say we have a 6-speed gearbox, then the max speed criteria will relate NT6 and ND, right? While gradability will relate NT1 and ND, right? So once again, we'll have 2 equations, 3 unknowns. So what do we do? So that's a question I want you to leave with. I hope the question is clear. All right. Okay. Yeah. Any questions? No. Okay. So if not, we will stop here. So we'll start off with the vertical dynamics in the next class. But anyway, we will briefly discuss this point before we go to vertical dynamics. All right. So if there are no questions, let me stop recording. Thank you.